Good morning. Today in this video lecture we will be discussing linear programming problem formulation, general, canonical and standard form. First we will discuss general form of LPP and then we will speak on solution, feasible solution, optimal solution, slack, surplus and artificial variable, and also we will speak on standard form, canonical form of linear programming problem through simple examples. Any linear programming problem, when you wanted to formulate for n decision variables, can be stated or expressed as, if it is a maximization or minimization, the objective function considering linear form can be expressed as z equal to c1 x1 and sum of c2 x2 sum of etc cn xn of all the multiples, where c1 c2 cn etc cn are coefficient multiples of each decision variable that is contributing to the objective function. Now this objective function is subjecting to m number of constraints. Let us say ith constraint which is ai1 x1 plus ai2 x2 plus etc ain xn, which is either less than or equal to or equal to or greater than to a particular resource value. The right hand side is indicating the resource capacity and which is contributing to the various decisions that we take for consuming this resource. And all these constraints I equal to 1 to m are constrained and the decisions will be taken for x1 to xn, and x1 to xn are all positive or otherwise greater equal to 0. That is why this particular constraint is called as non-negative restriction. So in a complete form, the general form of LPP appears like this: maximize or minimize z equal to c1 x1 plus c2 x2 etc cn xn, subjecting to m number of constraints and non-negativity restriction. Now this is expressed in matrix form, and that can be seen in the box here, where the function can be maximum or minimization, and that z equal to c to the power of t, that is a transpose matrix of cost vector and multiplied by the decision vector, subjecting to all the constraints, m constraints of that particular problem, and the decision variable values must be greater than or equal to 0. Now the basic definitions in a linear programming problem are solution, feasible solution and optimal solution. A solution is a decision vector which must satisfy all the constraints in the formulation, and also when it satisfies the non-negativity constraint, the third one which is then satisfying that, the decision vector is called as feasible solution space. Then solution, and also it is a feasible solution, then it should be minimizing or maximizing. If that is done, then that particular set of vector is called as the decision vector as a optimal solution for the problem in study. Let us summarize. The general form of LPP is having the following characteristics: the objective function is either maximization or minimization case depending upon the problem given, and the constraints of the problem are either in equality or inequality type. All decision variables pertaining to that problem are non-negative. Let us see some example, simple example, where when we maximize the function 3x1 plus 2x2 subjecting to constraint 1, constraint 2, and x1, x2 are decisions that are non-negative in the nature. Now if the point is given minus 3 by 2, 3 by 2 as a x1, x2 in your solution space, let us check whether this is a solution or a feasible solution or optimal solution. If you substitute this value in the constraints, so this should satisfy the given form of the constraints. If that satisfies, then that is a solution. If it is also satisfying given non-negative restriction, or other restriction, then that is called as a feasible solution. In this case, this satisfies all the constraints here, therefore it is a solution. Since it is not a feasible solution, because the given points are both negatives of x1, x2 values, so that is not permitted in this situation. Therefore, this is a case where there is a solution, but it is not a feasible solution. So, it never be a optimal solution. In the case, the same problem, if x1, x2 are declared as unrestricted, they are not restricted, then this point becomes a feasible solution. This point becomes a feasible solution. Even though it is a feasible, it is not a optimal solution, since this is not going to be generating the maximum value for the given objective function. Now, let us look at another example where we have 3 points of x1, x2 decisions, 0, 2, 3 by 2, 2, 1 by 2, 2.5 and 0, and it is in the solution space for the given problem maximization case, where maximize z equal to 1.5 x1 plus 2.5 x2 and so c1, c2 non-negativity restrictions. Now, if we substitute the given x1, x2 values in the given formulation, they satisfy the 0, 2 and 3 by 2, 1 by 2 satisfy both constraint set in the formulation and also non-negativity restriction. Therefore, they are feasible solutions. But when you try to look at the other point, the third point, which is given as 2.5 and 0, which violates the first constraint by not satisfying. Therefore, that is not a solution, that is not treated as a part of the solution space for the given problem. Now, in order to look at the standard form and canonical form, we need to look at other variables for the formulation. The slack variable is a variable we will be introducing in the formulation when we are converting inequality into equality. Let us say ith constraint, which is of less than or equal to type. That means the left hand side of the constraint is lesser by some value to the right hand side. That is a positive quantity. So, that has to be added. That has to be added to the left hand side, so that we can convert this inequality into equality. This particular positive variable here we are representing as Si is called as a slack variable. Now, in the case if the formulation has greater than or equal to type, then the left hand side is lesser by some number, greater by some number. That positive number to be subtracted from the left hand side formulation, and that variable is we are treating that because it is surplus to the right hand side. So, that is why it is called as surplus variable, and that positive quantity is subtracted, so that we can make it into equality, inequality into equality. Now, in the case when the variable is unrestricted, it can take, if it is not declared in the formulation, then that has to be defined, which is not defined in the formulation, then we need to treat it as a unrestricted variable. A variable x is unrestricted, then it can take any value, either may be positive or negative or 0. So, if x1 equal to x1 dash minus x1 double dash has a positive difference between two numbers is to be replaced in the formulation. The x1 will be replaced by two positive numbers, x1 dash minus x1 double dash. So, we will see in another example how this is utilized, and that is these two are the positive numbers. As a difference of these two positive numbers is representing xi, x1 or xi, whatever the in your formulation, and it is restricted. In this formulation, it is x1 is restricted. So, it will be replaced by x1 dash minus x1 double dash. Both are positive numbers. It can take any value, either it may be, but the difference can be positive or negative or a 0. So, canonical form of linear programming is called as when we have a function maximization, all the constraints should be less than or equal to type. If the given formulation is minimization case, then we need to have the constraints in the form of greater than or equal to, and all the decision variables are positive in nature. So, if we try to express in the matrix form, the canonical form, so this is the only simple modification. When it is maximization case, all the constraints are lesser than or equal to type, and if it is a minimization case, we will have all the formulation of constraints as a greater than or equal to type. Now let us see this through simple example. The general form of a given linear programming formulation. Here it is with the three variables. The objective function is with 3x1 plus 5x2 plus 7x3 and subjecting to two constraints c1, c2. So first constraint it is greater than or equal to type, and second constraint it is less than or equal to type. So when we want to write canonical form, so in maximization case we need to have all the constraints here lesser than. So we have here one constraint, that the constraint 1 is in greater than form, that has to be converted into less than or equal to form by multiplying -1 both the side of the equation. By that you will be changing the inequality from 1 greater than or equal to 2 less than or equal to, because that multiplication makes the left hand side is lesser. So with that we have the canonical form in this fashion. Now the minimization case, we need to have all the constraints in greater than or equal to form. So then one constraint here, the second constraint is in lesser than or equal to form, convert it by multiplying both the side with -1, and also we have x1 unrestricted, x1 unrestricted. So by placing x1 equal to x1 dash minus x1 double dash, this formulation, the 3x1 becomes 3x1 dash minus 3x1 double dash, and so on in the formulation. So now we have a variable space x1 dash, x1 double dash, x2 and x3 in the modified form after introducing the unrestricted variable formulation into the canonical form, and all the constraints are in greater than or equal to type. Now standard form of linear programming problem has the following characteristics. All the constraints have positive values at right hand side, and all the constraints must be converted into equality type, and all the decision variables are supposed to be positive or maybe 0. Otherwise there is no negative value is permitted in the decision space for your variables. Now this we will discuss through simple examples. Now let us say the previous problem where it is a maximization case and is subjecting to two constraints, as one is -1 on right hand side, other one it is positive value. So now all the constraints, the first requirement of your standard form, must be converted into positive on right hand side. So we will be converting that formulation into that first right hand side of the quantity is converted into positive by multiplying both the sides with -1. That gives us this formulation. Now after doing this, the second year statement it is we need to convert into equality type. Now we are converting that into equality type. The first constraint is lesser, so it is added by slack variable, and the second it is subtracted by the surplus quantity. So therefore we have S1, S2. So we are introducing in the order 1, 2 in the order of equations. The slack variable here it is S1, the surplus variable here it is S2 for the formulation. With that we have a additional two variables in the formulation, S1 and S2. These are not contributing anything to the objective function. If at all we need to place it as a 0 S1 here and also 0 S2 here, 0 plus 0 S2 in the formulation. That is what we have seen in our earlier one example. Now let us say where the variable is unrestricted, x2 is not declared, so it is undeclared, it is unrestricted. Therefore we need to convert the formulation with the additional x2 minus x2 equal to x2 dash minus x2 double dash. Therefore that brings us the formulation into this fashion: maximization z equal to 3x1 plus 5x2 dash minus 5x2 double dash plus 7x3 and all the other constraints. With that we have two variables, two positive variables in place of x2. x2 is replaced by x2 double dash and x2 dash. So we have x1, x2 dash, x2 double dash. Then we need to go for converting this into equality form. So surplus variable is subtracted here, slack variable is added here, so that we have now the variable space x1, x2 dash, x2 double dash, x3, s1 and s2 greater than or equal to 0. With this, we will conclude today's session. Have you have any query, please raise it through our WhatsApp group. Otherwise, when we meet in the next class, you can discuss with us. Thank you.